Hello, everyone. This is indeed a Ninja Stream DPI 209. I am currently attending the Planetary Science Institute's Citizen Science Conference right here in, oh my God, it's hot, Tucson, Arizona.
98 degrees.
I'm told that this is below average by like 10 degrees. I don't care, it's hot. But we're in air conditioning, and when I say we, it's because I have a special guest with me. This is Dr. Stuart Robbins of the Southwest Research Institute. He has worked on a variety of different NASA missions, including being the first person to get on his screen an image of MU-69. Now, here at CosmoQuest, one of the things that we invite all of you to do is help us map out other worlds. This guy's job is mapping out other worlds. You are a planetary cartographer.
I have branched into that field, yes.
So what does it mean? And here I'm going to be recording this, so I'm going to switch views. You're going to get more of us, and I'm going to hit record. So what exactly does it mean to be a stellar cartographer?
I have no idea, other than I'm a great cartographer.
Planetary cartographer. I'm so sorry. Let me try that again. What does it mean to be a planetary cartographer?
It can mean a lot of different things. Cartography is map making, basically.
Right.
So you can choose to make the base maps, which is what other people will then map stuff on, or you can map stuff. You can map stuff in terms of create a feature type database, or you could map stuff in terms of a geologic map. Most people might be familiar with, on Earth, we have political maps.
Right.
So that would be, where's the boundary of this country, where's the boundary of this state or municipality.
Yeah.
We do the same thing with geology as well. That's what a geologic map is. So we say this is a mountain range, or this is a river, or this is sedimentary rock, or volcanic rock. And so this is a geologic map. And all of this relies on different aspects of cartography.
And two of the things about this that amaze me most is, one, people have to figure out where to put the 0 point, and it's usually you find some easily seen but fairly small rock or crater, and you're like, okay, we're going to call this 0 and measure everything off of this. And then everything you do after that, you start out by doing it by hand.
Yes. So, funny enough, I was actually just at a talk last week, actually a conference before I came, well, not this last week, earlier this week, the Planetary Data Workshop. That was actually their 4th year. They go every other year. And there were plenty of talks there about setting that 0 point. It's
Wow.
there. You'd think that it's boring, but it's actually kind of interesting how they do that. So on Earth, there's just an international convention that we use Greenwich as the 0 degree longitude. But on any other body, there's sort of what do we kind of do? Yeah. So on some bodies, it is kind of easy because there's a subplanetary or sublunar point. So for example, there's the sublunar point facing Earth.
What does a sublunar point mean?
I have no idea, so I'm going to explain in terms I know.
Okay.
So it's the point of the moon that is always closest to Earth, or closest to Earth on average. So because the moon and the Earth are tidally locked, so they're orbiting, so the same side of the moon is always facing Earth, then we can say that that point that is sort of in the middle of that is the 0 degree longitude point. It's the same thing with Pluto and Charon. So we have the 0 degree longitude point set based on that. Same thing with a lot of large regular satellites around Saturn, all of the spherical ones, or many of them, they are also tidally locked. And so there's a sub-Saturn point, which is the point that is always facing the primary body most directly. But then you have other things like Mars. Okay, how do we set that 0 point? And it was actually sort of set by some French astronomers in the 1800s, And then it was sort of adopted by convention and it moved around. And once we got spacecraft imagery, we found a crater sort of near that location.
What could they see that they were going to call zero with the lack of CCDs we had back then?
You can resolve Mars in a telescope from Earth. So you can see different features on it. They're blurry and they're blobby, but you can see them. And so they saw this darker albedo, so a darker reflectivity patch, and said, the middle of that.
Okay.
And that was the 0 point. So when we got spacecraft images, it roughly corresponded to a crater that was about 500 meters across, which is small enough that at the time they said, okay, the middle of that's the 0 point. But then things moved around a little bit as we got better spacecraft data, and they had to keep shifting the 0 point. And now actually on Mars, I found this fascinating. The 0 point is not set at the 0 point. The longitude of the Viking 1 lander is set as something like 232.7 decimal points out degrees longitude.
Uh-huh.
That is the reference on Mars. And then you work it back, and that original crater is approximately at the 0 point, but they actually made an error based on obliquity shift. So Mars's tilt changes.
Right.
And there's a 100-meter offset, which is enough that the cartography people get annoyed. And so the International Astronomical Union is actually going to change where the 0 point is yet again. And actually that means where the Viking lander is. So that position is going to shift by the equivalent of 100 meters to make sure that that middle of that crater is at 0 degrees longitude. And the reason for the Viking lander is because it's smaller than the crater.
Right.
It's bright.
Right.
Relative to the rest of Mars, so we can actually see it more easily in telescopes on Earth just because it's a bright glint. And that's why they do it. So I bet when you started this a few minutes ago, you had no idea that I was going to talk about this.
Awesome. So I knew about the crater part. I did not know about the Viking lander part. And that's one heck of a way to reuse a dead spacecraft. So I approve. Archaeology for the win someday in the future. Now, it's not just about figuring out the 0 point to figure out where things are. One of the things that really got me the first time I saw a raw spacecraft image is as a spacecraft flies over a round world, the shape of the image changes so that when you're straight over what you're looking at, it's narrow. And as you're further away, it's wider. And so you end up with this bow tie shaped image. And then a world isn't flat. And it's not a perfect sphere. And
you don't have flat earthers on here, do you?
No.
Okay.
Or the mods have knocked them away. So you have to correct for the first approximation of round and then figure out what shape it actually is. Now, what kinds of things go into creating these shape models?
Oh, how much time do we have?
Just big picture. Just big picture.
It depends on what kind of data you have.
Okay.
So on Earth, we're really spoiled. So I'm not even going to talk about it because
Yes.
we don't do it the same way anywhere else because on
Right.
Earth we can actually go survey.
Yeah.
But around other planets, if you have a laser altimeter, we actually have had, I want to say 4 laser altimeters fly successfully at this point. So there was the Mars Orbiter Laser Altimeter about 20 years ago. There was the Near Shoemaker Altimeter. So that's why we have such good shape models of the asteroid Eros.
Okay.
That was also in the 90s. And we have the MLA, which I call bleh. It flew on Messenger, so it was able to ping the surface, and basically by measuring how long it takes to go there and back, so the total flight time, divide that by 2, divide that by the speed of light, and you get the distance.
Right.
And then you have to, of course, know where your spacecraft is in order to also
Small
figure
problems.
that out. And we also have currently active on the moon, the LOLA, Lunar Orbiter Laser Altimeter. It's returned over 7 billion laser points. In contrast, so that's the active mission at the moon right now. On Mars, MOLA, an earlier version of that, returned over the course of 2 years about 600 million. So we're at over an order of magnitude more. And actually there's a fifth. There's OLA, which is on OSIRIS-REx.
Oh, yeah.
And Ola is really weird. So instead of just pinging the surface with a point, so Mola is a single point. Lola is an array
grid.
of 5,
Yeah.
which I can sort of do with my fingers, but not really. Yeah, something like that. Maybe. Ola, it like splits it up into like hundreds of little points.
Oh, wow.
And it's almost like a grid from a single shot. I don't quite understand it, but I haven't really looked into it that much. That was a large digression on lasers, so that's the most direct way. We call that an active topography or an active system because it is shooting something at it. Another way is passive.
Yeah.
So this is usually what people think of as stereo.
Mm-hmm.
So if you take 2 images from slightly, well, actually there's a whole bunch of math, so it's not slightly, from different positions, it's basically like just cover one eye and cover the other eye. Something near versus far is going to shift when you do that. So it uses parallax to calculate the shape and the topography based on those 2 images. There's also shape from shading, also known as photoclinometry. So this is where just if you know the angle of the sun or angle of the illumination source and you assume a certain reflectivity and a certain way that material reflects light. So for example, metal reflects light different from plastic.
Yes.
And every planetary body is different.
Yeah.
So there's other assumptions and math that goes into this. But you can basically build up a shape from the brightness of the pixels in a single image. So from all of those different methods and planetary science, we combine all of them or as many as we possibly can, given the data that we have and the quality of the data that we have, in order to build up that 3-dimensional shape. And then when you take those images from a spacecraft, because the detector is flat and it doesn't know how everything is shifted and tilted and oriented and then how it would need to be draped over the topography.
Right.
We have software that we use. The United States Geologic Survey's software is the main one that people use, I think. It's called the Integrated Software for Imagers and Spectrometers. It was a name made in the 90s. It had issues about a decade ago because the acronym is ISIS.
Yes. Yeah. I've only ever heard it called ISIS, but you're right. You can't say that anymore.
Right. So in all of my grant proposals, it is ISIS 3 because it's the 3rd version.
Fair.
So ISIS does all of that math for you. So it has the shape model for most bodies. It has the IAU radius, the International Astronomical Union, which by convention sets a radius for the planetary body.
Yeah.
It can do all of the camera geometries. It can take those raw images and it has a camera model. So cameras distort images.
Right.
They're not perfect. The optical system distorts things and you have to correct for that. So it has all of these things built into it. And so you can actually take a raw spacecraft image and out the other end, you can get a nicely, properly projected image.
And this really brings home why computer scientists take so much math. Because this software does more geometry than I hope to ever have to do again. So for those of you joining late, I am, as always, Dr. Pamela Gay. I am your host. Joining me today to talk about all the things that go into, well, building our maps of other worlds is Dr. Stuart Robbins from the Southwest Research Institute up in Boulder, Colorado. Now, so far we've talked about how you find the 0 point, how we figure out the shape of an object, which is a constantly upgrading thing. The shape that you figure out in 2010 will have evolved for, like, the moon by today dozens of times.
Oh yeah, so I could talk more about that. I'll try to shrink it to a minute because this is actually kind of interesting. So let's say you have all the data you want in terms of you have laser and you have stereo.
Yeah.
And you have an image. So let's say you use the laser for your shape model and use stereo for your shape model and you get a shape model. Then you take an image and you project it onto the surface and you take another image and it projects to a different location even though they should project to the same place. You can use software in ISIS to correct for that, which corrects for the spacecraft position and pointing, which means that any contemporaneously taken data, like your laser altimetry or your images you're using for stereo, also gets slightly updated, which means that you need to redo your shape model. that you're draping your images over, that you're using for the alignment, that you're using to work back the spacecraft data, and you can get into an infinite regress here.
It's turtles all the way down.
Now, most people will stop at step 2. But,
Yeah.
but there are people at the United States Geologic Survey who argue vehemently that you need to actually do this kind of iteration at least a couple times. But they're the people who care about placing things at the meter level, as opposed to, I'm more concerned these days about hundreds of meters. So, most people are more concerned about hundreds of meters. But when you're working at a landing site, it becomes important. Because
and this is what we're doing right now with Bennu mappers, is we're trying to find not a landing, but a touch and thieve site. Because
well, more like a...
It's kaboink. It's a kaboink.
Well, but they're going to blow.
Right.
And that's how this... So it's like
and then suck. It's an angry vacuum cleaner. This is my view.
I'm picturing Spaceballs right now.
As you should. As you should. Now, you and I first met in 2009 up in Colorado when I was attending an Astronomical Society of the Pacific meeting.
I had more hair then.
You did, but I was much thinner then, so times have changed.
We all grow as we age, just not necessarily in the proper direction.
It's true. You never finish growing. Now, when I first met you, this was when I really learned how much science is done by hand. I'm an astrophysicist. I like to put apertures on things and count photons. I get sad when my machine learning won't do things for me. And back then we couldn't measure galaxies without using volunteers. Now machines have got all that stuff. But with the kinds of things you do, we still aren't there. And when I first met you, you were in the process of drawing over 3 million circles on Mars. Literally.
You're off by an order of magnitude, but that's okay.
30 million?
No. About 600,000 on Mars.
But I know you drew a lot of the circles more than once for comparison data.
Well, I did it in images and I did it in topography, and I had to go back and redo my work.
So how many circles became your catalog?
There are about 620,000 in my Mars database, but I have a lunar crater database of over 2 million.
Okay.
So it's a lot of circles.
All hand drawn.
All hand drawn.
Can you show the...
I'm supposed to show my... without making an obscene gesture.
Well, hold 2 fingers up, maybe.
This is...
Yeah.
Okay. So I have a little hump on my... I need to cut my fingernails, but I have a hump on my finger. That's a big callus, because I use a pen tablet input device.
This is part of why I told all of you doing Bennu mappers to get a Wacom tablet if you have one. I learned that trick from this guy. Now, you are one of many crater counters in the world where this is what you do. Well, it's greater than 3.
It's greater than 3, but probably less than 30.
Yeah. And the questions that we get around here include things like, so we have all this laser data. Why don't lasers just tell us where the craters are?
I'm not sure how a laser would tell you where the craters are.
Well, explain. So if the laser is, and this is the way people always ask it to me, if the laser is telling you exactly how far away the surface is from your spacecraft, won't the laser be able to go higher here, slope, 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 flat base, and higher, higher, higher out of the crater?
What's the difference between that and a mountain range?
That's true. But aren't craters circular?
They are circular. Yes. They're actually not perfect circles. There are extremely few that are perfect circles. So automated crater detection, which is what I assume you're going after.
Yeah.
It's so many words. Automated crater detection is something that people have been trying to do since computers were invented, pretty much. So there's a guy who works in my office who finally sort of retired. I cite a paper of his from 1967 to give you an idea of how long he's been working on this stuff. He wrote a Fortran, or maybe it was on punch cards at the time, computer program back then to try to identify impact craters. And the problem is that craters are not a simple circle, and they're not in isolation,
Yeah.
and there is underlying topography going on, and craters are more complicated. Even if their rim is a perfect circle, they're more complicated on the inside than just a perfect circle. Or what if you have a crater on the interior wall of another crater?
Yeah.
Then it's not even a rim is the same elevation kind of situation. So even today, even with machine learning, and there have been a lot of people contacting me over the last few years about, oh, I have this wonderful new algorithm that has discovered all of these craters, and it's wonderful, and I've compared it to your database, and it's wonderful. And you look at the details, and it's not so wonderful.
And some of the problems that we run into is, well, the laser data has a resolution bigger than the smaller craters. Humans all make mistakes in slightly different ways, and the software that is trying to use human data to learn is just sort of like, wait, what do you mean this crater should be shifted slightly to the left and this one should be shifted slightly to the right? There's different color soils on these worlds. There's different textured soils on these worlds.
When you have a situation of just simply picture a big crater like this, because I don't have bigger hands. This is my big crater, and then a little crater that's the size of
Here, let me do this.
Okay, so that's our big crater, and then this is our little crater, and I'm putting my little crater right here. How is a computer algorithm supposed to identify those separately? It's going to see a weird part of the rim and think that, okay, maybe something happened, but why would that be a different crater? Or let's say you have two craters like this.
Right.
We see a lot of these kinds of situations, a lot of this kind of overprinting. And in a lot of these machine learning, a lot of these automated crater databases, they have to feed the computer images at a bunch of different resolutions.
Right.
So stuff is fed at, it's maybe a 256 pixel by 256 pixel, which I know seems really small, but apparently there are limitations even today. So they feed them these small images, and maybe they'll feed them one set that's at 10 kilometers per pixel,
Right.
one at 5 kilometers per pixel, 2.5 kilometers, and 1 kilometer, and so on. And then once the machine has come out with all of their detections, they have to cluster them in order to merge them into a single database. And once you start to cluster, you have all of these free parameters that you deal with. And so a cluster is normally going to say, well, two craters like this is probably one crater. Or if it's not one crater, then it's going to find, so the machine found the same crater here and here.
Right.
And so now if you've told your clustering code, no, that's really two separate craters, then you're going to have a false positive. So you always have these kinds of problems, which is why I've actually been working with a computer vision guy from Silicon Valley who does facial recognition research, and he actually kind of wants to get out of it because he's concerned about the inherent racism and how these things are trained. So craters are raceless.
But they aren't planetary-less.
Right, so they look different on Mars from Vesta from the moon, but he's interested in this kind of stuff, and he's been going to some of the crater meetings, and so we met and we've talked, and myself and another person where I work are working with him to try to develop a hybrid approach.
Right.
So I think that I am probably one of the fastest manual crater people out there.
Yeah.
I can do craters at around 1,000 an hour. Most people, it's a few.
He's faster than CosmoQuest people.
So most people who do this for a living are maybe a few hundred an hour.
Yeah.
I've seen some people get faster these days. Some people claim to be close to me, but never quite above. But that's a separate thing. But so my point is that the way I do craters is I trace the rim of the crater, and then I do stuff with the rim. I fit a circle, I fit an ellipse, I do other kinds of stuff with it. What the automated crater detection tries to do is it tries to both find the crater and size the crater. And that initial finding is really, really hard.
Yeah.
So what I've told him is, hey, instead of we do everything or you do everything, let's merge the approach. We will point at the center of a crater. You can even give us an approximate scale. So again, scaling those images.
Right.
So you know that there is a crater roughly centered here of roughly this size, within a factor of 10 or something,
Yeah.
or 5, whatever the computer needs. Then you take that and find us the rim. And we think that that kind of hybrid approach, it's never going to be as fast necessarily as a wholly automated approach.
Right.
But we crater counters are anal people, and we like to be correct. And so the problem is that we don't ever, and will probably never, trust that fully automated approach anyway, especially because there's this 50-year history of it failing. So if we have an approach where we've already told you the crater is centered there and it's roughly that size, and live, especially with modern GPUs, because a lot of this can be GPU accelerated with machine learning, live, if I click there, and almost instantaneously it traces out my rim, and I can say yay, nay, or I can just not even do that. I can just say moving on, and not even say yay unless it's a nay, in which case I cross it out. I could do probably upwards of 10,000 an hour, because it's just click, 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 and in 3 seconds there, I've done 20 craters.
Yeah.
So I can do so many more, and we still get the fun machine learning part, because some people are into that.
It's true.
And we still get the accuracy, because we have done the craters ourselves, but we've also live checked it as we go, as opposed to all me tracing it or having to trust a catalog that I know is going to have issues like this clustering issue or something else.
Now, Astro YYZ in the chat is asking, what makes the human being so much better suited for mapping craters that differentiates us from the computers, especially with all these deep learning algorithms out there right now? It's our brain is just still better.
The eye-brain combination is so much better at pattern recognition.
Yeah.
The issue is that stuff is noisy.
Right.
So if I were to present you a perfectly clean, pristine surface, say a fresh, young volcanic lava flow, which we might have some of them in Tucson where we are.
Yeah,
I
it's
think
true.
These are, I know in Flagstaff, 4 hours north, all those mountains are volcanic, which is really cool. That's a separate issue. So if I give you this very young, pristine lava flow, and I have a single crater on there, everything can detect it. You can detect it. I can detect it. We'll probably get almost the exact same diameter. The machine can detect it because it's a simple circle on nothing else. But as soon as you start to pepper that surface with a lot more stuff, and then you have crater rays, and you have ejecta blocks on top of it, and then you have a grainy image, and then you have, well, that image was actually taken when the spacecraft was looking like this as opposed to straight overhead, so you have smear and emission angle weirdness and other things going on. Your human eye and brain can still say, that's a circle, that's a crater. But the computer has to make choices.
Yeah.
And those machine learning things, the convolutional neural networks, which is all the rage these days, it's what all the kids are talking about.
Right.
So those CNNs are good at what they do.
Yeah.
But what they do is a little bit of a black box. So they've work on a training set. So I have fed it what some craters look like, and then you have to reserve some of those known craters in order for it to try to classify, because there's this issue of overtraining, which I didn't understand until talking with these folks. So overtraining is where you basically fed it too much training data. And because you've fed it too much, all you've done is you've trained it to just identify those exact things.
Yes.
And you don't want to do that. You want to keep it general. But these CNNs are basically, it's all of these layers upon layers of turtles making decisions about which way we're going to go. And those decisions are a total black box. And so if you find out that it's detected this crater correctly but not this crater, you can't go in and change it. Whereas a more traditional approach you could.
Right.
The approach now you can't. And someone in the chat mentioned CAPTCHA. This is actually something we talked about at the Planetary Crater Consortium meeting last year. And yes, there really is a Planetary Crater Consortium. We meet every... I completely losing my train of thought.
When you got to talking about machine learning with craters and overtraining and undertraining.
Right. Well, so we want to try to figure out a good approach that actually solves the problem for everyone. We don't want to overtrain, we don't want to undertrain, but we also need to get some way of figuring out what a good way to get these training sets are, and good training sets, because right now, to be perfectly honest,
There aren't any.
my crater data is the only training set that kind of exists, because they need tens to hundreds of thousands of consistent craters, and especially if we want to detect the rim,
Yeah.
which you can do a heck of a lot more science if you have a trace of that rim rather than just there be a circle here.
Right.
If we have that rim trace, we can do more, so we want that rim trace. My data is the only stuff out there.
And your data doesn't go all the way down in the resolution. And unfortunately, the way things look, it's not purely fractal. It isn't purely a 1 meter crater looks the same as a 100-meter crater.
Right, and so this idea, now we remember where my train of thought was going, we actually kind of jokingly said, does anybody have a friend at Google? And we can get a CAPTCHA system going.
Yeah.
Because there are so many, every day practically, I have to click a CAPTCHA to do something
Yeah.
or other, identify crosswalks or identify stairs. And it's like, does this image have a crater?
Right.
And that kind of thing would actually help towards this sort of system. It wouldn't necessarily give us a rim trace, but it would get us partway there.
And this is where some of you may have encountered in EVE Online. There's been some crater tracing there, and we are always trying to find a better way to solve this at CosmoQuest. And the problem we run into here is we love all of you, but you haven't marked millions of craters yet, so you're slow. I still love you. And so with this problem of how do we get enough data quickly, and craters aren't as easy as galaxies. I can very easily write software to look across an image of the night sky, zoom in on the brightest points, draw a box around those for where the brightness drops down to the sky level. And what's inside of that box, if it's round and matches the point spread function, is a star. If it is weird and blobby, it's either a galaxy or a nebula. And there's certain regions on the sky where statistically it's going to be a nebula and statistically it's going to be a galaxy. Now, galaxies don't come in that many shapes in the grand scheme of things. And since it's a bright pattern on a dark surface.
That's the key.
Right. Now with craters, you sometimes have a light crater on a dark surface, you sometimes have a dark crater on a light surface, you sometimes have both occurring simultaneously.
Look at Sharon.
Oh my goodness.
But the problem with these craters is that it is not there's not a dynamic contrast there from
Right.
the surrounding surface. What you are looking at with images is you are looking for that bright shading on the sunlit side of the rim going into shadow, and then bright shading on the sunlit side of the rim going into shadow.
Yeah.
And that brightness difference might not be more significant than the brightness difference from something else.
Yeah.
Or it might be impacted by a crater ray. Or on the moon we have cryptomare material, which is where you have buried lava flows that basically get exposed and blown out from a formation of another crater. And so you have these brightness changes that are real to the surface that are not reflected in what your eye brain can do in terms of shape for shading, or shape from shading.
Right.
So your eye and brain are doing this photoclinometry, and that's how we detect those crater rims so much better than a computer can. And even we make mistakes. So usually you have to redo your first couple tens of thousands of craters. I saw something funny a few weeks ago. It was doing a dissertation is like doing a group project where your partner is you from 5 years ago when you had no idea what you were doing.
Yeah, and you spend so much time the last year of your dissertation going back
And fixing it.
and redoing what you did the first year. For me, it was reducing images.
For me, it was redoing craters.
Right. Now, with all of these craters that we're measuring, each world looks different. We're currently, as a community on CosmoQuest, struggling with the fact that on Bennu, The easiest way I've found to identify a crater is it's an area where the insides are more crushed and you usually have a ring of small rocks.
Bennu is weird.
Oh my goodness, yes. Yes.
Yeah, I don't try to do craters.
Don't.
There. No.
You don't want to. But looking out, you've done craters on Mercury, Mars, the Moon, and Pluto.
And Charon, and
Yeah.
ME69, and moons of Saturn.
And with all of these objects, it's not like we're going to go try and grab a soil sample from Charon anytime soon. What are we learning from all of this data that you're helping us have?
So it depends on what body you're talking about.
Right.
Because the state of the science is so different
Yeah.
depending on where you are in the solar system. So for example, in the outer solar system, especially with Pluto and Charon and ME69, we don't know what the size distribution of objects is. So we don't know, for example, what that means is we don't know how many more smaller objects there are than larger objects, because we know that there are more smaller than larger. It's just how collisional physics
Right.
works. You take a brick, you smash it, you are going to get more smaller pieces than large.
Yeah.
It's the same thing with rocks and ice balls in the outer solar system. So the sizes that we can probe by looking for tiny specks of light from Earth are bigger than what we can probe with what made craters on Pluto, Charon, ME69. And so what we can do is we can work back the size distribution of the impactor population.
So basically, we can find out how many small rocks there are and how many big rocks there are that it's hitting things.
And that has implications for how the solar system evolved and how the big planets might have done a little dance early on in the solar system, and how things might have scattered, and how things might have been built up
Right.
over the course of the early solar system. So even though people say, craters in the outer solar system, who cares? They're actually really important because we don't know that kind of stuff. I mean, craters in themselves can be interesting science, especially if you want to understand how bombs work, for example.
Fair.
Which was something that people did in the 1950s and 60s. They studied craters in order to understand how bombs work and the explosive capability. So they can be important in themselves, but usually they're a means to another end.
Yeah.
So in the outer solar system, again, a lot of it is trying to understand the size distribution of objects. So we don't know it. We want to understand if there are different impactor populations in the outer solar system, so we can compare craters on the moons of Saturn with the, I was going to say moons of Pluto. We can't, I did map those, but there are very, very few. So on Pluto and Charon.
Right.
And then we can also compare those to the inner solar system. So there's still some crater people who say you can take the moon and go everywhere in the solar system.
Yeah.
They're wrong. I'm going to say it now. You can't. But all the crater data show that. And so we can also do this on Ceres and Vesta. So we can see what the impact history of those have been. And again, we see a different shape in terms of the number of large versus small features. And all of this matters. So for example, we can also look at the transition of where we go from a simple bowl shape. There we go. Wow, I'm not as flexible as I used to be. A simple bowl-shaped crater to a more complex crater, like ones that have a central peak in the middle.
Yeah.
I need to remember that demo. I just thought of that. So you go from a simple bowl-shaped crater, like literally looks like a cereal bowl that you plunked in the surface. Someone says crater people. So you go from a simple bowl shape to one where it looks more flat floored. You have a central peak. You might have steeper walls.
More like Gale Crater.
Like Gale Crater. So on Mars, that transition is roughly around 5 to 6 kilometers. On the Moon, it's about 15 to 20. On Vesta, it's so big that we don't see it.
Wow.
On Ceres, it's a different size.
Yeah.
And so you can look at the transition diameter and you can understand stuff about the surface gravity, which we already know from other methods.
Right.
But once you account for surface gravity, you still get differences. And so that tells you what the material strength is. So for example, that transition diameter in sedimentary rock versus crystalline rock, like a granite on Earth,
Yeah.
is different by a factor of 2. not factor of 2, factor of 50%. It's like about 3 kilometers versus about 2
So
kilometers.
this is hitting sandstone versus hitting,
a mountain.
yeah, Canada, the Canadian Shield.
Or Russia, Chelyabinsk.
Fair.
Yeah. Or
yeah.
Africa. Yeah. Anyway,
Yeah.
let's stop bombing countries. Sorry, political statement of the day. No, so you can look at the differences there and understand the material properties versus water. So, I mean, a simple thing would be go out, take a rock, throw it into a pond, assuming you're not in Tucson where there is no water. So throw it into a pond, and you'll see that central peak.
Yeah.
Now, it'll immediately collapse because it's water and it can't hold the shape. But then do the same thing into a pile of sand, and you're not going to get that central peak. You're just going to get a bowl, and that's because the material strength is different of sand versus water.
And if you have a small child that you're looking to occupy, you can go from a bowl of water to a bowl of thick cream like you're going to use to make whipping cream, to you can mix up cornstarch and water, and then you can do all sorts of cool stuff. But as you go through all these different materials that have what are we call different viscosities, you can see differences in how things go splat. And who doesn't love throwing things into bowls of fluid?
And a PSA about whipped cream. So make sure that you buy something with a milk fat above 30% if you want to whip cream. Because I accidentally bought table cream once, and I thought that was whipping
No.
cream. The milk fat was about 15 to 20%, and it would not whip. These days, I go with 35%.
So now you know, folks. Making that whipping cream, make it right, use the real fat. Okay, so we're running out of time, and there's one final thing. You've been part of New Horizons. I remember going into the encounter, you thought that it would be a, oh my God, sleepless days of trying to figure out ages from all the craters we expected to see. What was your first reaction when you saw that Pluto was just like, hey, my surface is younger than bees?
Initially, I was like, wake me when I'm awake, because I was really tired when those images came in.
Mm-hmm.
It was exciting. It was interesting. I was still sleep deprived, and my mom called me the next day, upset that I would be out of work because she had read news reports that there were no craters on Pluto. That's not correct. There were no craters found on the large ice sheet that we think is a nitrogen ice convecting glacier. But there are
This
plenty.
is the heart.
Well, part of the heart.
Yeah.
The other part of the heart is something else.
Okay.
We think that and that's a separate discussion. But there are well over 5,000 craters on Pluto that we were still able to identify and catalog, and well over 2,000 craters on Charon, plus a few dozen on Nix, and I think 4 to 6 on Hydra, because the imaging wasn't as good. So there was still work to do, but it was interesting because it was, they always say Pluto defies expectations, but to some extent, it did, but to another extent, people don't understand these days that we go into these missions thinking we're going to see stuff that we never even thought possible, but yet when we're interviewed and we're asked, well, what do you expect to see? We have to come up with something. And so the answer that one of the New Horizons co-Is said at a press conference in, I want to say early 2014, maybe, at NASA headquarters, she said, I expect to be surprised and to see something. And the interviewer didn't like that.
Yeah.
But it's like, yeah, that's what I kind of expect. So I got what I expected. I was surprised.
Yeah.
But Alan Stern, the mission PI, liked to contrast it with Mars because it was done on the 50th anniversary of the Mariner 4, I think, flyby of Mars. And so people had these expectations for what they were going to see on Mars. Like, it was informed by popular culture at the time. Maybe we'll see plant life and other things. Going back to Percival Lowell's days and Giovanni Schiaparelli.
Yes.
And canals and other things, and maybe we'll see plant life. And we saw a dead cratered
Yeah,
landscape.
yeah.
Now, granted, Mars is a lot more interesting than that. There's cool stuff on Mars. Get me wrong. I got my dissertation, PhD with Mars. But with Pluto, we got kind of the opposite. It's like, wow, we knew it had an atmosphere, but we didn't know that it had 50 plus layers in the
Yes.
atmosphere. We didn't know how extended the atmosphere was. I mean, it's basically the atmosphere scale height is huge compared to the body itself. We also did not expect to see a glacier that's
Right.
less than 1 million years old. We did know that it was bright. In fact, this is an unsung tale. A lot of people don't know this. We specifically planned that the encounter hemisphere, so the hemisphere that we would get the best images of, were going to be right along the brightest area, because we had done surveys with the Hubble Space Telescope and mapped out the brightness on Pluto and Charon and planned the flyby around that. So we expected to see something interesting there. Probably no one expected to see a nitrogen ice glacier in an 800-kilometer wide basin. But we saw that. We also knew ahead of time there were brightness differences, huge brightness differences. So that was not unexpected. But that contrast and seeing it up close and seeing that kind of stuff was unexpected. But
it was awesome.
We expected the unexpected, just
Right.
not that kind of unexpected.
Now, the one thing that we totally knew would be happening is this kind of ruined the 4th of July. And then MU-69 totally ruined New Year's.
I would say ruined. I mean, it depends on what your definition of...
As a journalist, I grow embittered. As a scientist...
As someone who didn't have to visit their in-laws?
Fair. So it's one of these things where, did you know going into planetary science that you were going to be turning over your holidays for the exploration of the solar system?
No, but it's also a choice.
Yeah.
I could have chosen not to participate.
Yeah.
In fact, I made a concerted effort to participate. Wow, my hands looked huge. Okay, sorry.
Oh, so we've learned you can do infinite arm with the camera. The closer you get, the longer your arm appears.
Forced perspective, yay.
Yes,
okay.
sorry.
So, hi, everyone. So no, it was a choice, and I fought for that choice because it's fun to be a part of that kind of thing.
Right.
And especially when you're an early career scientist, I mean, you know, inside baseball here, it's good to be known as a team player, as someone who is willing to make those kinds of sacrifices, so that you can be included on more interesting or similarly interesting, we'll go similarly interesting, future stuff and future opportunities. If you're known as the person who always stays home and values this, that, or the other thing, then you don't necessarily get those opportunities. And that's a good thing and a bad thing. A lot of issues these days are about maybe we need to try to re-emphasize and go back to the drawing board of a work-life balance in science, because there isn't one.
No.
I mean, I remember, so my dad just recently retired. He was is a, because he is not quite retired, PhD medical researcher, cardiologist, but not an MD. He doesn't do any of that icky dissection or operating stuff.
Yeah.
Vivisection.
He's on the gross anatomy side of things.
It is gross. But yes. So I grew up with a scientist in the house, and it was normal that my dad would not be there when I woke up.
Right.
And that we would be eating dinner late, 7-ish or so. Usually my dad would call in the afternoon saying, "Honey, I'll be home at 6 or 7 or whatever." And that was when my mom, knew to start making dinner. And to be perfectly fair, she also had her own career, at which she decided it was her choice to leave to raise the career to raise children, and then develop a different career, and now is on a 5th career. I don't know. So that aside, I grew up with that kind of situation, and I do remember that there was a year where my dad said, "How would you guys feel if?" Because I have a brother. "How would you feel if I did a sabbatical in someone else's lab, so I'd be gone for 6 months?" And at that point, I was just like, "No." I had a decent relationship with my parents. They were always, especially during the teenage years. But, I kind of said, "No, I'd rather you be here."
Yeah.
And so he didn't take it. But still, it's even the long work hours. So, and I bring my work home. So I live 45 minutes from the office.
Yeah.
And so I don't go into the office most days. I work from home, which is great on the one hand, because it means that I save an hour and a half in commute.
Yes.
But on the other hand, I have a situation where, for me, there almost is no separation between work and life. So I will basically, the way my day normally goes is I'll get up around 11, 12. No, I'm a late sleeper. So I'll get up around 10-ish on a normal day. I'll work for 2 or 3 hours. Then I'll do something else for an hour. I'll work for 4 hours. I'll do something else for an hour or two. I'll work for 5 hours and go to bed maybe around 1 to 2 a.m. And so for me, that works, but there is no work-life separation. And with missions especially, taking this back, with missions, you really do have to decide, do I want that work-life balance, or do I want to be involved with this kind of mission? Because to be perfectly honest, that's how it works these days.
And CosmoQuest in some ways is a mission where you guys with the launch of Venue Mappers know that I was online writing software at all hours to keep things going as you threw ideas my way. We still are implementing them. Bear with me. It takes time. Now,
as someone who spent all day yesterday and the day before programming,
yes,
it takes time.
I have my PHP Storm open in the background. But you do find time in stolen moments to still do some cool stuff outside of your day job. Your photography is awesome, and you've done a podcast over the years. So
we're currently on hiatus.
Well, that's why I said over the years. So where else can people go besides the journal articles to find the stuff that you're communicating out and sharing with the world?
So I do have a blog archive, we'll say, because I haven't posted in 2 years. So that would be pseudo-astro, Pseudo, astro.wordpress.com. The podcast website is, I can probably type it faster.
We're gonna type these into the chat.
The podcast website would be podcast.sjr, so my initials, design.net. I came up with that because
you also do graphics, and you're
and I figured it was general enough. That it would not haunt me in a decade.
True.
But also I've been involved with a podcast recently. I won't say it's a competitor to Astronomy Cast, but it's a similar kind of thing, although it's much shorter format. And we do seasons.
Oh, cool.
So we just put out the second season a month ago. It's called Astronomy in 5.
Cool.
So it's 5 minutes with an astronomer, although this season that was much more in name only. So 10-minute, 15-minute episodes, but it's the idea is just like Astronomy Cast. We tackle one topic per episode. So it's with some Canadians. So yes, Canadians. They're a fun group of people.
And Astro YYZ is a Canadian.
Right. So this is the Reality Check podcast people. So 2 of them, music people, and they've been kind enough to host me twice, and we just go to their basement and over 3 days record way too much, and then one of the guys edits it and we put it out. We just this season interviewed, I can never remember his last name. He's the lead singer from Bare Naked Ladies. Ed something. Ed Canadian. So we interviewed him, and he asked a question for the show. So we talked about where does space begin, basically, a topic you've done. But he has astronaut friends. So he had basically been in a conversation with Chris Hadfield, being like, so have you actually been to space? Because Earth's atmosphere goes halfway to the moon.
Right.
And so that was a topic that we talked about. And then Ed is really big on pseudoscience, which is my cup of tea. I like using that as an example for where thinking goes wrong, to use that. Ed Robertson, yes, thank you. I like to use pseudoscience as a way for to explore how people's thinking goes wrong in order to sneak in real science. And Ed is really big in the same venue of combating pseudoscience. And so after we got that question in about where does space begin and the atmosphere, he just went on like a 20-minute, I won't say rant, a 20-minute story about he was getting his hair done, and his hairdresser was a flat earther. And so we just talked about that for a while. So that's in this past season.
That's
so that
cool.
would be astronomyin5.com. You can
Okay.
either use the number 5 or the word 5. Either works. So I don't think I need to type it in. I'll just say it again, astronomyin5.com.
Available where podcasts are archived.
Not sold.
Yes.
There are no commercials. There is no charging.
Perfect.
Although the reality check does have commercials in it.
And so what's the next kind of research that you're looking forward to getting your,
Oh.
Wacom into?
So the topic, bringing this way full circle to 50 minutes ago,
Right.
The thing that I've been getting into for the last year and a half is cartography.
Yeah.
So I have been trying to do this issue of bringing those images together. And so there's a problem of we have the spacecraft data, so we know where the camera was told to point. We have radio tracking of the spacecraft from Earth.
Uh-huh.
And so when ISIS-3 projects those images onto the surface, they should be aligned properly.
Right.
This crater should be where this crater is because they're the same crater.
Yeah.
And this is important because I want to redo my Mars crater database with
Oh, wow.
better data, because the data I used by current standards is
Old.
old. Yes, we'll use that word.
Yes.
The newer data are more gooder, basically. The problem is that if I identify a crater in one image, it is in a different location in another image. And that's not good.
No.
This gets
no.
to our definition of zero and longitude and
Yeah.
latitude and all this stuff. So I have worked for the last year and a half to try to develop as automated software as possible to do that alignment process on the Mars Reconnaissance Orbiter context camera images.
Okay.
So these are 6 meters per pixel. 6 meters for you Americans is America and Belize
It's about 19 feet.
and Liberia.
I know.
I think are the 3 countries.
I know.
So 6 meters, yeah, about 19 feet.
Yeah.
So a large double couch.
Yeah.
For example, these are amazing pixels, amazing pictures
With amazing pixels.
with amazing pixels of Mars. It is a nearly global data set, better than 98% coverage at 6 meters per pixel.
Dang.
So it would be a great data set, over 8 terapixels. That's
A
8
lot.
trillion
Yeah.
pixels, a lot. Again, the problem is that alignment. And the
Yeah.
problem is that when people do this kind of alignment, it's mostly manual still. I've been
And then you get human error.
I've been working to develop these automated tools which do it faster with established workflows that people trust, and I've been trying to get it funded. So I'm not here asking for donations. I'm not doing that. But I'm saying if any NASA reviewers happen to be listening, my process works. The thing
Yeah.
is that basically a lot of people get embedded in how they do things.
Right.
And they don't necessarily think outside the box. And then you have someone else saying, well, there has to be a better way to do this. And there has to be a way, even if we can't update some of the core software that tries to match features and do this other stuff and solve for where the pictures really should be.
Yeah.
Even if we can't update those core programs, maybe we can update the way that they're called and the way data are fed to them. And that's what I've been doing. And I've gotten it so that it's really, really fast compared to the way people do it before. So we think we really can do it in a 3-year NASA proposal. And so I've been making the rounds at conferences trying to show that we can do this, because right now the proposal is good. The work is good. We can do it. It's more of an issue of convincing the community.
Yeah.
Which is an unfortunate part of our job, is that sometimes as a scientist, you have a really good idea and you have a really good workflow that you know works. But if you haven't quite convinced the panel and they haven't seen your work, especially if it's so new
Yeah.
compared to what their established methods are of doing things, they won't be convinced. And so you won't get funded. And so this
There's
gets into
bias
a
in
separate
science.
topic.
This is bias.
Really? There's bias?
Just a little, just a lot.
Anyway, that was, again, longer than was probably needed, but I've been getting into cartography.
And that's awesome. So we look forward to seeing what all you have coming out in the future
Me
and
too.
continuing to find new ways to, well, prove that planetary scientists are really programmers who just program other worlds. So this has been fabulous. Do you have any parting words you want to leave for our audience?
I'll do my TRC sign off, which
Go
is
for it.
remember, kids, science doesn't suck; it blows.
It's true. And this isn't the last Ninja stream of the day. I am probably going to be back in about 15 to 20 minutes with NASA Ames programmer, scientist, Brian Day. And we're going to be talking about ways that you can explore surfaces using software available on the web. So, as always, this is a production of the Planetary Science Institute working in collaboration. Well, actually, we're not right now, but the channel in general is working in collaboration with Youngstown State University. With me today was Dr. Stuart Robbins from Southwest Research Institute up in Boulder, Colorado. And wherever you are in the world, remember, you can get outside and look up and enjoy this universe we all share. So I'm not going to go away. I'm actually just going to throw up the away from keyboard screen. And thank you for those cheers, Astro YYZ. So I'm going to switch over to our AFK screen. And I will see you all in just a few minutes. Don't go anywhere. Grab a drink. We'll be right back. Looking for the button. back. I am by myself. Despite being in the same time zone as the next person I'm interviewing, I managed to give time zones. He is going to be here a little bit after 4 Pacific time. So in roughly an hour, we will be, well, roughly an hour and a half probably, we will be back with one more ninja science engagement. So go away, but come back. And I will be sharing out on Twitter when we're getting ready to go live. Maybe use the time to map some Bennu. We're getting close. We're getting close. Everyone do 15 more images and we're done. Anyways, I will see you all on the other side. Bye-bye.